Hello and welcome to my presentation on efficient parameter estimation for multiple class monotone missing data. So to start, the motivation of this work is that the assumption of equal covariance matrix is usually needed in linear discriminant analysis or hypothesis testing or when the sample size is small. Another thing is the popularity of the monotone missing data problem, especially in longitudinal studies where the information on a set of cases is collected repeatedly over time. For example, in a Parkinson study, all variables from the first block can be recorded at the beginning of the research and fully observed. The second block, recorded 2 years later, may not be fully observed, as some of the patients have left the study. The third block of the variables, recorded 3 years later, can increase in missing values due to addition. Next, we have a definition of a monotone missing data pattern. A dataset with ordered features V1, V2 to Vp is said to have a monotone missing pattern when the event that a feature Vj is missing for a particular sample implies that all subsequent features Vk, where k is bigger than c, are missing for that sample. Alternatively, when a feature is observed for a particular sample, it is assumed that all previous features Vh, where h is smaller than j, are also observed for that individual. As in an example, we can see that the dataset in equation 1 is a dataset of 4 features with a monotone missing pattern. Another example can be seen here. This is a dataset of 8 features with a monotone missing pattern. So we can see that the stars form like a staircase at the bottom of the dataset. So now let's talk about parameter estimation for two-class monotone missing data. To start, we have the data partition procedure. Suppose that we have a D which consists of Y and Z. It's a two-class dataset. Here Y contains the first class samples and Z contains the samples from the second class, and each column corresponding to a sample. K is the number of blocks. There are n1 observations on the first B1 variable and n2 observations on the first B1 plus B2 variable, and so on. So we can partition y into y1, y2, yk as in equation 3 to 6. We can see that y1 consists of this row, and then y2 consists of this row and this row with columns from this column to this column, and so on. And finally, yk consists of the first k columns. And we can partition Z similarly into Z1, Z2, Zk. As a specific partitioning example, suppose that we have a dataset in equation 7 where y and z are as given in equation 8. Then we can partition y into y1, y2, z into z1 and z2 as in equation 9 and 10. So one can see that y1 contains the first 2 rows of y, y2 is the first column of y, z1 is the first 2 rows of z, and z2 is the first column of z. We have some more notations and definition. Now assume that each sample in Y for the normal distribution with mean mu and covariance matrix sigma, and each sample in Z follow a normal distribution with mean eta and covariance matrix sigma. So that means that they have the same covariance matrix. And now let yi bar and si be the sample mean and covariance matrix of yi, ci, and ri be the sample means and sample covariance matrix of zi. And we define the sum square and cross product matrix wi as in equation 11. Next, let sigma I be the leading principal submatrix of sigma of size sum of pj times sum of pj for any I in 1 to k. Now we partition mu into k non-overlapping partition. Note that k is the number of blocks, so we partition according to the size of the blocks. Each mu bracket j is a vector of size pj times 1, and then we let mu I to be the vector that contains the first I partition of mu. And then we partition xi bar, sigma I, and wi as in equation 13. So yi is partitioned into the first part and the second part, where the first part has the sign of sum of pj, which is from 1 to I minus 1 times 1, and the second partition has the sign of pi times 1. And the partition of sigma I is had the size relevant to the partition in yi bar, and similarly for wi. With this way of partitioning, we can realize that sigma I bracket 1 1 is equal to sigma I minus 1. So this allows us to compute the estimate in a sequential way, and we can create similar partition for ci bar and eta. So as a specific example, we have a computation diagram for k equal to 4, which means we have a 4 blocks. Then we will partition the mean of the first class into 4 non-overlapping partitions as in equation 14. And to estimate mu, we will first estimate mu1, which is equal to mu bracket 1, and then we will estimate mu bracket 2 based on mu1, and this gives us mu2, which is this part. And then next we will compute, we will estimate mu bracket 3 based on mu2, and this will give us the mu3. And finally we compute mu bracket 4 based on mu3, and this provides mu4, and that is also equal to mu. The computation progress on the covariance matrix is also similar. So first we will estimate sigma to bracket 1 1, which is this one, and it is also equal to mu to sigma 1. And then we will estimate the remaining blue part based on this one, and this provides us sigma 3 bracket 1 1. And next we will estimate the green part based on the blue part, and that gives us sigma 4 bracket 1 1. And finally we compute the yellow part based on sigma 4 bracket 1 1, and this provides us the whole sigma. For specific formulas, we have the following theorem, which states that the MLEs for the two cascades can be explicitly expressed as in equation 15 to 18. So we can see that mu1 hat is estimated by y1 bar, and then we estimate mu hat bracket I sequentially as in equation 15, and then a similar procedure is done to estimate eta. For the estimate of the covariant matrix, we first estimate sigma 1 hat based on W1, and then we estimate the components of sigma I based on equations 17 and 18. Here Bi and Qi are given us in equation 19. So based on this theoretical insight, we have the following algorithm for the estimation of two-class monotone missing data. So first we will initiate mu hat and eta hat, and then sigma hat in the equation 20, and then for I from 2 to k, we will compute Pi and Qi based on equation 21, and after that we can update the means and then the covariant matrix, the partition of the covariant matrix, and then update the covariant matrix based on equation 23.